My name is Henning Lange, and I'm going to present to you in the next couple of minutes a paper that I just recently finished with my collaborators Steve Brunton and Nathan Kutz. So the archive identifier is right here, but you can also find a link below in the description. So what I'm going to talk to you guys today about is, it's very fundamental and it's a very simple idea. So I'm going to introduce algorithms that can do the following. So you present the algorithm with data, temporal data, from time point t equals 1 to time point t equals capital T. And what the algorithms are going to do that I'm going to introduce today is they're going to predict these temporal snapshots into the future. And what the goal is of these algorithms is to go very far into the future. So we want to go like 10,000 steps into the future, which is approximately 1 year at an hourly sample rate. And this obviously doesn't work without making any assumptions about the data. So we make the following assumption, namely that the temporal snapshots are produced by a quasi-periodic system. So I'm going to introduce two algorithms. The first one we call Fourier forecast. That algorithm is similar to the Fourier transform, but it does not make implicit periodicity assumptions that would be harmful for forecasting. And the second algorithm that we call Koopman forecast is in general based on Koopman theory, and you can understand it as the Fourier transform in a nonlinear basis, in a nonlinear and data-dependent basis. So the optimization objectives of the algorithms are pretty nasty. So the Fourier forecast algorithm has a non-convex objective, and the Koopman forecasting algorithm has a nonlinear and non-convex objective. And even though the objective functions are pretty hard to solve, we can find global optima in the direction of some of the parameters by using the fast Fourier transform. So on like a meta level, what I'm going to do in this task is explain the ways in which we compute the parameters that govern the temporal evolution of the algorithms. So the algorithms have hard to compute parameters and easy to compute parameters. And I'm always going to talk about how to obtain the hard to obtain parameters. And I also am going to talk about how to obtain a single one of them. And in order to optimize all of them, we just apply coordinate descent. So, and what these algorithms are doing like on a meta level is they alternately optimize hard and easy to compute quantities. But in this talk, I will only talk about how to obtain the hard to optimize quantities. So, okay, let's get to it and talk about the first algorithm that we call Fourier forecast. And what we're trying to do is the following. We have our snapshots xt, like they're just measurements. And we're trying to fit a linear dynamical system yt to our temporal snapshot xt. And we're introducing two constraints. And the first constraint is that yt evolves according to a linear dynamical system. And the second constraint we're introducing is that the real part of the eigenvalues of this matrix B that describes the linear dynamical system are 0, which basically means that the system does not crash into the origin, so it doesn't go to 0, and it also doesn't blow up to infinity. So it's a stable system, which basically fits the data that we are trying to model, namely quasi-periodic systems. So when you look at this optimization objective, you can rewrite it in this way. So the constraint that the eigenvalues of the matrix B are purely imaginary turns yt into a vector that only contains sinuses and cosines evaluated at specific frequencies. And in this case, the easy to compute quantities is the matrix A, but the hard to compute quantities are omega I. So in order to avoid basically the notational clutter, we call this vector that contains the sines and cosines, we just call this capital omega. So the nice thing is, because A is linear and omega describes a linear dynamical system, we can actually find an analytic solution for Wi. And basically what comes out is if you solve this optimization objective is a very nice symmetry relationship to the Fourier transform. So if you solve this objective for omega I, what you basically get out is the following. The orange graph shows this error function, and the blue graph shows the Fourier transform. So colloquially speaking, if you take the Fourier transform, you move it up on the y-axis, and then flip it on the x-axis, you get the error surface. So now let's go back and look at the assumptions that we make about the data. The assumptions that we make about the data xt is that they stem from a quasi-periodic system. And we can show, so basically this is known in electrical engineering, that if you have a quasi-periodic system, its Fourier transform is going to be a superposition of these sinc functions. So how do we optimize our objective function? So if we were to use the fast Fourier transform, which evaluates the Fourier transform at integer multiples of 1 divided by t, we always get frequencies that are periodic in t. And that's not a very good property if you're trying to forecast. Now, what would happen if we would use gradient descent? Because the superposition of sinc functions is super non-convex, gradient descent will very quickly get stuck in local minima. So what we end up doing is we're combining the strengths of the two optimization procedures in order to solve this objective in the following way. So we use the fast Fourier transform to locate the valley in which the global optimum resides. And this will give us a frequency which is periodic in t. But then we use gradient descent to improve this initial guess provided by the fast Fourier transform to break this implicit periodicity assumption. And graphically, this looks like this. So the blue line that you see is the data that we were provided with. And the orange line below, this is the error surface that we can compute. So what we do is we use the fast Fourier transform to locate this valley and put back our initial guess for gradient descent right here, and then using stochastic gradient descent, improve this guess and wander down this error surface. And that is how we improve a single omega I. Which brings us to the next algorithm, which is the Koopman forecasting algorithm. And so the Koopman algorithm is based on Koopman theory. And in 1931, Bernard Koopman showed that you can take any nonlinear dynamical system and apply a nonlinear but time-invariant function to the measurements of this nonlinear dynamical system and lift it into a space where its time evolution can be described by linear methods. And there's a very strong analogy to Kutz theorem, which is arguably the theoretical underpinning of kernel methods in deep learning. So Koopman theory tells us you can take a nonlinear dynamical system, apply a function f, and in this transformed space, we can describe the data by linear methods. And the same is true for Kutz theorem. Kutz theorem says you can take any data set that has two classes, project it into a high-dimensional space, and there will always be a space in which we can linearly separate or describe the data with linear procedures or linear methods. So this is just a quick reminder. This omega t that I introduced earlier is a stable linear dynamical system. And we go into the reasons why we do that a little bit more in more detail in the paper. But the objective that we're trying to solve for the Koopman algorithm is the following. It's essentially the same as the Fourier algorithm, except for one difference. instead of a linear link between the oscillator yt and xt, we assume that there's a nonlinear function f parameterized by theta that links the data and the oscillator. And so why do we do that? So one reason is it gives us noise robustness, which I'm going to go into a little bit more detail later. And another reason is it's more expressive. So if you have a square wave, you would need infinitely many Fourier modes to describe this data. But in the Koopman framework, you only need a single oscillator and a nonlinear function. So that's the whole idea. So, and in this case, f theta is usually a new network parameterized by theta. And in this case, theta is like the easy to compute quantity, or like the easy to obtain quantity, because we can just use stochastic gradient descent. But because of this nonlinearity, this analytical solution that we exploited for the previous algorithm, it doesn't work anymore. So the symmetry relationship between the Fourier transform and the error surface just doesn't exist anymore. So now we have a problem. We have an optimization objective that's not only nonlinear, but is non-convex. However, we can still compute the global optima in the direction of omega I. And how we do that is by exploiting periodicities in this error function. So let's take a step back. So the error function we're trying to solve is a sum of what we call temporally local loss functions. So we're summing up this L for every time step. Now let's have a look at this loss function at a specific time step in a little bit more detail. So if you look at this temporally local loss function, it's very easy to show that this loss function is periodic in 2 pi divided by t. And this follows almost directly from properties of the sine and cosine function. So what this looks like graphically is the following way. So on the first graph shows the temporary loss function, the temporally local loss function for t equals 1. And it makes 1 revolution over the span from 0 to 2 pi. The loss function at t equals 2 is going to make 2 revolutions. The loss function at t equals 3 is going to make 3 revolutions, and so on and so on. So how do we exploit the periodicity in those temporally local loss functions in order to solve for omega I? What we do is we just sample this loss function for every t in this, within 2 pi divided by t. And then we have all the information we need in order to solve globally for omega I. Because what we need to do is, once we have the loss function computed within the first period, we can just take this period and just copy and paste it over and over. So what we need to do is repeat the loss function t times. But then, because we want to sum all of these loss functions up, we need to resample them to have like the same sampling interval. And the last step is just to sum all of them up. So the result usually looks like something like this. So it looks very similar to like the regular Fourier transform. The nice thing is that this repeating and resampling is very, very easy and efficient to implement in frequency domain. It's basically one for loop. Okay, so now I showed for 2 algorithms how to compute the global optimum with respect to omega I. Let's have a look at what these algorithms do. So we have a couple of results. Some of them are theoretical and some of them are practical. I'm going to start with theoretical results. And so one of the results is that the Fourier algorithm, the linear Fourier algorithm, has universal approximation properties for finite data sets. So if you give me a data set from 0 to t, I can always overfit on the test set. And that follows very, very simply from just basic properties of the Fourier transform. And it's also analogous to Kutz theorem, because it also requires projecting the data into an n-dimensional space. And just like Kutz theorem, this trivial solution just does not generalize. So it's not a very useful property in practice, actually. So if we have a look at infinite data streams, then the Koopman algorithm is more expressive than the Fourier counterpart. And this is due to a fact that I alluded to earlier, namely that for some signals, the Fourier algorithm would need an infinitely big parameterization, where the Koopman algorithm would require only a finite dimensional parameterization. So the algorithms that I introduced today, they have a very close relationship to Bayesian spectral analysis. And because of this relationship, we can actually prove error bounds fairly easily. So what we can show is that the prediction error, is going to grow linearly with t. So the further you go out in your prediction, the higher the error will be, but the error grows linearly, and which is a very nice property. And another nice property is that the performance degrades also linearly with noise variance. But the algorithm scales super linearly with the amount of data provided, so capital T over here. So it grows linearly with t, but it shrinks super linearly with the amount of data provided. So let's try to predict a very simple nonlinear oscillator. So this is a nonlinear oscillator that has like fake temporal patterns that mimic basically temporal patterns at an hourly rate. And we compare the Fourier algorithm and the Koopman algorithm to LSTMs. And how we are doing that, because LSTMs are usually not meant to do long-term predictions, is we take the prediction of the LSTM and feed it recursively back. So we're integrating out the LSTM. So on the x-axis, you can see the prediction horizon, basically the further you go out. And on the y-axis is the cumulative error. And LSTMs are doing pretty badly, and the Koopman algorithm does better than the Fourier algorithm. So let's try to understand why this is the case. So these are the actual predictions in time domain. And so this is the prediction horizon. And in the beginning, all of the algorithms are doing fairly well. However, if you go out pretty far into the future, then things start to break, and they break differently. So LSTMs seem to be a biased frequency estimator. So the LSTMs get the nonlinear shape right, but they are slowly going out of phase, which is catastrophic if you're evaluating how good your algorithm is with a mean squared error. So it would be better for the LSTM to just predict 0. So why does the Koopman algorithm do better than the Fourier algorithm? The reason is the Fourier algorithm needs a lot more Fourier modes to appropriately model nonlinearity. And the small Fourier modes, they get drowned out by noise, and you can see like the small Fourier modes just slowly drifting out of phase. And the Koopman algorithm, because it can explain the nonlinear shape with actual nonlinearity, does a lot better. It's more noise robust. So let's have a look at, so this was the synthetic data set, but something very similar happens when you look at a real data set. So we took a data set that contains the energy consumption of a node in the German electrical grid at an hourly rate. And it's the demand of a node in the distribution network. And this data has lots of temporal patterns. So energy consumption usually is lower on the weekends compared to weekdays. That means we have like a weekly cycle. Then we have a typical daily cycle because energy consumption is usually highest around like 2 p.m. And then we have obvious seasonal patterns because energy consumption is, in Germany at least, usually higher in the winter compared to the summer. So we have all of these like temporal patterns, and there's also a lot of like structural noise because the energy consumption depends on weather, which is kind of hard to predict. So if you look, so these are the results in frequency domain. And so in order to like support the claim that I made earlier, you can see that the LSTMs seem to be biased frequency estimators. So they're close, but they're not perfect in terms of getting frequency right. So why does the Koopman algorithm in this case does better than the Fourier algorithm? And the question is why. So I'm not sure how well visible this is, but the Koopman algorithm can explain very small harmonics just with a pinch of nonlinearity. And if we would try to model these with the Fourier algorithm, it wouldn't work because they would get drowned out by noise. So the Koopman algorithm gives us noise resilience. A lot of fluid flows are nonlinear oscillators. And we can model nonlinear oscillators with our algorithms. So we took a simulation of a flow around a cavity, and I think this is Reynolds number of around 1,000. And we can almost perfectly model what's going on. Let's summarize what I presented to you today. So today I introduced two algorithms to fit linear and nonlinear oscillators to data. The objectives are non-convex and nonlinear respectively. So there's a ton of like real-world phenomena that are quasi-periodic and basically fit the inductive bias of the algorithms that I introduced today. And examples are, for example, gate, then weather or space weather. Tons of fluid flows are quasi-periodic. They're periodic systems. Epidemiological data, because it's called the flu season for a reason. So lots of applications in power systems, sales. For example, the occupancy in a room is somewhat periodic. And if you have a phenomenon that fits this quasi-periodic characteristic, then these algorithms will work well. So the code is available on GitHub. And if you have any questions, please feel free to email me. And I'm very thankful for your attention.